Okay, so I went back and forth on this, and I just decided that work and power is too important to completely skip. So we're gonna do like the 1 day version before we jump into torque, and then we're gonna do 2 days of torque, and that's it. And then on Friday we are going to start reviewing for the final. On Monday we'll review more for the final, and on Tuesday the final will be available, but you don't have to complete it until the end of next week. So um, the final will be available starting Tuesday of next week, and you'll have Tuesday, Wednesday, Thursday, and Friday to work on it. Ask me questions, ask each other questions, and make sure that you're all ready to be successful. So, like Tuesday of next week, if you don't feel like you're ready for it, we can keep reviewing, and I'll have review material available. Or Tuesday, if you want to just start taking the final, and then if you get to a spot you don't know, then you can go back and keep reviewing more. That's what I would suggest. So next week is the final. This week we have just two more things we have to learn, and this one's pretty straightforward. Work and power is very straightforward, just like energy. There is one slight trickiness to it, just like energy, and that's why I wanted to include this little video. It'll actually teach you some more about vector math, and how vectors actually have mathematical operators that are slightly different than regular numbers. So we'll go over that. So I want to make sure I don't send you off to college without having any exposure to work and power, and it teaches us some math you probably haven't learned before as well. Um, that's cool too. So I know I can't decide what I want to do this week, and I was going back and forth on whether or not to include work and power, and I've decided that just 1 day work and power is kind of necessary for me to really call this a good physics class. So today's that day. The objectives today are all about work and power and what they are and how to calculate them. So that's the goal for the video here today. So when you hear the phrase do work, what comes to mind? That's the first question, is what does work mean to you? So think about that for, I don't know, 10 seconds, and then I'll put up some images of what it means in physics. So let's see what some of these ideas here. You may have thought something like that, but that's not what we're talking about in physics. We're talking about work that's used to move objects. Moving items is the work we're talking about here. So lifting the barbell, moving the giant Newton's cradle, dragging the box, all of those are examples of work being done in physics. So things are pushed, pulled, dragged, essentially when forces are used to move items, and that's key. Movement is key. If there's no movement, then physics speaking, no work has been done, and we'll go over that. So using force to move objects, and by doing so, you actually transfer energy into the object. So it's a transfer of energy that involves motion. That's what work is. So work is actually measured in joules, just like energy. So you use up a certain amount of joules of work. Let's use cars as an example. So your engine, let's say, does 100 joules of work, then that means your car has gained 100 joules worth of kinetic energy. Now that would be if your engine was a perfect translator of energy. Obviously some is lost to friction and this and that and the other things. So, probably if your engine did 100 joules worth of work, your car would probably get, 90 joules of kinetic energy or something. But essentially that's what work is. It's the ability to add or remove kinetic energy from objects using a force. That's what work is. And so that's just what I exactly said, but now we can see the words for it. So work is energy transferred to objects to influence movement. So in the study guide, the bowling ball going down the alleyway example, friction is doing work on that bowling ball in order to slow it down. So friction is doing negative work in that case because it's removing kinetic energy. The kinetic energy change of the ball is negative, and therefore that would be a negative work done by friction in that case. So when energy of an object's changed through a force, such as friction, that's how you know work has been done. And to calculate work, you take the displacement vector, so again, displacement vector, and multiply it by the force in the direction of displacement. And that's where vectors start to matter a little bit more than just regular numbers here. Because look at this example here with this guy carrying this box. You can see that he's doing a force to lift that box. The blue force here. That force is being done to lift the box entirely in the y direction. The displacement, once he's lifted the box, so lifting the box did indeed take some work. But now we're not looking at lifting the box. He's lifted the box, he's holding the box, and now he's just walking to the right there. He's not actually doing any work on the box to hold that box that whole time, because the force is entirely in the y direction and the displacement is entirely in the x direction. There is zero overlap at all. So it's because none of that force is in the direction of movement, is in the direction of displacement, there is no work being done. So you need to use trigonometry, right? So say we had an angled force here. Say it wasn't straight up and down. Say this was our force. Then you would need to use cosine to figure out how much of that force was in the direction you want, and that's the amount of force you use. So direction is important here. Your force vector and your displacement vector have to be in the same direction. If not, you need to use sine or cosine to make it that same direction. And so let's go back to our original example here. We've got this force straight up and the displacement straight to the right. That makes a 90-degree angle, which we can show using a square just like that. So it's a perfect 90-degree angle. So this force here is at an angle of 90 degrees with our displacement. So, and they're adjacent, right? They're touching. So you would do cosine of 90 degrees, which turns out to be 0. Cosine of 90 degrees is 0. And we can see that, right? That's a mathematical way of saying what we just learned. That because this force and this displacement vector are completely in different directions, no overlap at all, then the work being done is 0. And mathematically, that's because cosine of 90 degrees is 0. So that all makes sense. But basically, long story short, you only care about the amount of force that's in the same direction as displacement. Any force that's going in, so say your displacement's in the x direction, any force in the y direction, we don't care about. It does not impact our work. So in order to calculate work, it's force and displacement, and you may need to use sine or cosine in order to get those to be the same direction. And it makes more sense if we see it in action. So I think the next slide goes into that in more detail. So this slide dives into what we were just talking about with the force being in the same direction as displacement. So let's look at that. Let's draw some example arrows here. So we've got force right here. Let's call that our force arrow. I'm just drawing some random arrows. And let's say that this was our displacement right here. This was force on some object. And the displacement, however, was not in the same direction as the force. And we want to know how much work did that force, how much work did that force do on the displacement? How much work did the force do on the displacement of that object? What was the impact of that force on the object in terms of work? So you can see here that this force has a y portion and it has an x portion because it's at an angle. Well, the displacement here is entirely in the y direction. There is no x component of that displacement. So we need the y direction component of the force. Well, when you look here, right, at our angle, that's adjacent. The displacement vector and the force vector are touching the angle there. So that they're adjacent to each other. And they'll always be adjacent to each other in this case, which leads us to the mathematical formula. So let's call this theta here. This angle is theta. We don't know what the angle is. We're just going to call it theta degrees. So this is called the dot product. That's where this big dot in the middle, F dot D. That means that we want to take the dot product of these two vectors. What is a dot product? The dot product is exactly what I've been saying here this whole time. It means you take two vectors and you want to multiply the components of one of them onto the other. Think about it this way. You've just like it says at the bottom, right? Think of it just like x and y directions. When we had forces at an angle, we used sine or cosine to figure out how much of that force was in x and how much of that force is in y. So likewise, we can use sine and cosine, right? This up here forms a triangle, just like we're used to. So we can still use sine and cosine to do that, to figure out how much of this F force here is in the D direction. And because the D vector and the F vector are touching, they're adjacent, adjacent goes with cosine. So dot product is simply equal to the force vector times the displacement vector times the cosine of the angle between them. And that's what I wanted to show you here. If that makes sense to you, then you'll be good to go for college. And let's add our vector arrows to our vectors to show that we're dealing with vectors here. Both F and D are vectors. So to calculate the work done by a force on an object, you take the strength of that force and you dot product with the displacement vector. What does dot product mean? What we just said, right? You take the force, the strength of the force, the magnitude in newtons, you multiply by the length of the displacement vector in meters, and then you multiply that by the cosine of the angle between them. So that will work every time. You don't have to SOHCAHTOA, you don't have to draw triangles, it's always cosine. The force and displacement will always be adjacent angles. That's just the nature of the universe. That's more of a mathematical concept than a physics concept, to be perfectly honest. So I'm not going to get too far into it. Just accept it that it's true. I promise it's true. It's always cosine. To take the dot product of two vectors, you take the strength of the two vectors multiplied together, and then you add in that cosine component as well. That gets the angle in there too. So that's the dot product. That's work. That's all you have to do to find out, okay, how much work did gravity do on, so an example problem here that you might see is, let's say we've got a mountain, a very steep mountain, and we've got a guy skiing down the side of it. Woo! I'm getting pretty good at this whole mouse drawing thing. So you got a skier skiing down the side of a mountain there. Gravity is obviously going straight down. Whoops, I'm still struggling to draw straight lines here. But let's make gravity green, green for gravity. And gravity acting on the skier is going straight down, right? Because that's what gravity always does. Gravity doesn't care if you're on a mountain. It's going to pull you straight down towards the center of the earth. Friction, let's go purple for friction. Friction, however, is always going to be exactly backwards, right? So if he's going down the mountain forwards, friction's going to be trying to slow him back up the mountain there. So friction, is in the same direction as motion, basically. It's backwards, so it's in the negative direction, but essentially it's in the same plane, right? If we call down the mountain x, right? If we say this guy is going down the mountain in the x direction there, then friction is also entirely in the x direction. So we don't have to do any sines or cosines other than remember it's negative. So technically, actually, let's look at this. Let's look at this. I'm glad I brought this up. This is going to be a useful conversation. So let's look at this free body diagram mode without the actual picture there. That's the guy's velocity vector, his displacement vector, right? He's going down the mountain, d. So that's the displacement vector. The friction vector, the friction force, is exactly opposite to that, right? Here's friction. So what's that angle, right? What is our angle here? If we're talking theta, what is our angle? Our angle is 180 degrees, a complete turnaround. If you're familiar with like skateboarding or snowboarding, you know a 180 is when you flip around and you're going the other way, or you turn around. So this theta is not 0, it's 180. That's good enough, actually. Actually, that's pretty good. My drawings are getting pretty good today. So you would take your force of so say we wanted to figure out how much work is friction doing on the skier. So the skier's gone down the mountain, let's say 100 meters down the mountain. So that would be our D, our displacement vector would be 100 meters. And friction, let's say, had a strength of 20 newtons. I'm completely making up numbers. I don't know if these are reasonable numbers or not for skiing. 100 meters would be a pretty short ski run, but maybe a bunny hill. So we're on the bunny hill, and he's gone down the bunny hill, the beginner's hill, and he went down 100 meters, and friction had a strength of 20 newtons, and we want to know how much work did friction do. So we would do force, which was 20, so 20, times displacement, which was 100. Oh, let's keep my colors consistent. So displacement, and I'm not going to include units this time just because I'm trying to speed up. So 20 times 100 times cosine of the angle between them, which was 180 degrees, right? Because they're pointing exactly opposite. So cosine of 180 degrees. And it just so happens that cosine of 180 is -1, which is where the negative comes in. So negative work means it's trying to slow the object down. It means that it is a force that's resisting motion. So friction, you can set up a very weird situation where friction actually does positive work, but that will never happen in this class, let me tell you. So most of the time friction is doing negative work because it's slowing the object down. So negative work means that it's a force that's trying to slow the object down, that it's going against displacement. Positive work means it is speeding the object up because it's going with displacement. So again, positives and negatives mean a third thing now in physics, right? Usually they mean direction, like positive direction, negative direction. With charges, it means charge, right? Positive charge, negative charge. Now here with vectors, with work, right, we have something new called a dot product, where now all of a sudden positive means speeding up and negative means slowing down, and it kind of has to do with direction, but not the same way. So I hope all of this made sense. I think the drawings are pretty good. The examples we came up with together are pretty good. So the answer then in this case, why don't we put this all together and get a final answer? And the answer to that one, 20 times 100 times -1. Remember, cosine 180 is -1. So 20 times 100 is 2,000. And then times -1 gets you -2,000 joules of work. So that answers the question. So again, the question was for the skier going down the mountain here. This right here, the skier going down the mountain. He goes down 100 meters, and during that time, friction has a strength of 20 newtons. And the question is, how much work was done by the frictional force? And so we plug that into our work formula, force times distance times cosine, and we got -2,000 joules. And again, negative means it's slowing them down. It's resisting motion. That's what negative means when we're talking about negative work. So if you have an object going to the right, a force going to the left would be doing negative work. A force going to the right would be doing positive work. So negative work means slowing down, positive work means speeding up. It's a shame that physics needs to use those same positive and negative symbols to mean so many different things, but when you think about the situation, it makes sense. Let's take a look here at gravity in this situation. What kind of work is gravity doing? So again, let's look at our free body diagram here. We have displacement vector, which is not a force. So technically that shouldn't be on the free body diagram, but because it's a work problem, we do need to see that displacement vector. So I'm going to include it. So we've got displacement there, which is not a force. Remember, it's a distance. It's in meters, not in newtons. So there's our displacement. And then gravity is going straight down. And so if the question was, what would be the work done by the force of gravity in this case? Well, you would need to know this angle right here, the angle between displacement and gravity. If you knew that angle, then you could still plug it into that same exact equation, where now F here would be the strength of gravity, right? 9.8 times the skier's mass. D would still be 100, because that's the displacement. And then cosine would be the cosine of the angle, whatever this angle right here is, the angle between gravity and the displacement vector. And then that would be a positive number in this case. Any cosines between 0 and 90 are positive. And then, well, 90 is 0. So any cosines between 0 and 90 are positive. And then any cosines between 90 and 180 are negative. So since this is a less than 90 degree angle, we know it's going to be something positive, which makes sense, right? Like they're kind of heading in the same direction. They're not perfectly heading in the same direction, but they're generally going in the same direction, whereas friction is clearly going in the opposite direction. That it's force times distance times cosine of the angle between them. That's the formula for calculating what you need to know about work. So if it's asked how much work was done on something, that's how you calculate it. Force dot distance, force times distance times cosine. Another thing that might be asked of you is this. Friction did, so let's say a ball started with 200 joules of kinetic energy. Friction does 50 joules, negative 50 joules worth of work on this ball. How much kinetic energy does the ball have left? It would be 150, right? It had 200 joules of energy. Friction did negative 50 joules of work on it, so it stole 50 joules of that energy from it. And then, so the ball was left with 150 joules of kinetic energy, and then you could use the energy formula to find the speed even as well. So that's where you'll most often find these equations used in real life scenarios, is either figuring out how much work was done by a certain force, or if we know how much work was done, we can calculate either the displacement, right? So that's one way we can find, like, stopping distance is, okay, we know the force and we know the work, what was the distance? You can calculate speed, right? Like if friction stole a certain number of joules of energy, you could find the new speed of an object. But it all comes down to work and this formula right here. So let's maybe look at some examples. So here's an example problem. We have 60 newtons of force used to move an object of a distance of 4 meters. And this is very straightforward, right? It's just force and distance, no angle between them, so we can assume it's the same direction, right? So we've got 60 newtons of force, and we've got a displacement in the same direction there of 4.0 meters. That's technically a 0 degree angle, right? These two arrows are pointing the exact same way. So if we were to draw them on top of each other, right, you would have, here's your force, and then here's your displacement, and there's no distance, there's no angle between them at all. So that would be a 0 degree angle between them, technically. So just for completion's sake, let's do the full formula. So work equals force vector. Work is not a vector, by the way. Work is just a number. When you take the dot product of two vectors, you're left with just a number. It's no longer a vector. Force dot displacement, which we know equals force times displacement times cosine. And I'm just going to leave it in variable form for now. So there's our general equation. Force times displacement times cosine. And so in this case, that's going to be 60 times 4 times cosine of 0. And for those of you, hopefully, if you've taken trigonometry or geometry, hopefully you know your unit circles. Sorry, that's an S, not a 5. But cosine of 0 is 1. The cosine of 0 degrees is 1. So this equals 240, right? 60 times 4 is 240. Times, and then cosine of 0 is 1. And that just gives us a final answer of 240 joules. of energy that was transferred. So let's say you were pushing a box and you were pushing with 60 newtons and you moved that box 4 meters. You have done 240 joules worth of work on that box. You have successfully transferred 240 joules of kinetic energy from your body, your chemical energy, your cells and your muscles, into the kinetic energy of that box. So when you were done with that, if there were no friction somehow, if you were pushing this box along a frictionless surface somehow, then when you were done doing this, the box would be moving with 240 joules of kinetic energy. However, in the real world, friction, as you were pushing, friction was constantly stealing that energy, turning it into heat and sound. So it's very likely that maybe the box slid a little bit, but didn't really keep sliding. But that's just the real world. If we were on, say, an ice surface, if we were able to do this on a hockey rink or something like that, then when you were done, the box would be moving with quite a bit of speed still, because all of that work you did to put energy into the box, that energy doesn't just disappear, right? Friction can waste it over time, but it doesn't just disappear. So if you were on ice or something slippery, that box would continue moving with quite a bit of kinetic energy because of the work you put into it. So work is kind of like a form of energy. It shows energy being moved from one object to another object through a change in kinetic energy. That's what work shows in physics. Joules, again, don't forget your units. Force is in newtons, and we want our displacement to be in meters. Joules, newtons, meters, seconds, kilograms. Units are very important in physics, so we don't crash our space probes into Mars, which I'm sure I've told you that story before, so I won't go too far into it again, but classic story of NASA not converting its units correctly and they crash a probe. So make sure your units are good. Always make sure you've got meters, seconds, kilograms, newtons, coulombs, joules, the units we've been using. Another example problem here, just to make sure we've got it, but again, it's just force times distance times cosine, but in this case, again, it's cosine of 0, so 1. So just 2.5 times 800, and I'll let you work through that yourself. Great, so pause the video now if you're not ready for the answer, but 2.5 times 800 is a cool 2,000 joules of work that was done to lift this person. So let's talk a little bit about power now. That's work. I'm going to try to go quickly for power because power is much more straightforward. There's no dot products or anything like that. That'll take me 20 minutes to teach you. Power is very much just an equation. You take your work and you divide it by the amount of time spent. So if you did 100 joules of work in 10 seconds, your power would be 10, just 100 joules per 10 seconds. So done over time, it is the time derivative. If you want to get into your calculus terminology, power is the time derivative of work. It tells you how quickly work is being done. It's the slope of work. So if work is being done very, very quickly, you have a high power. If work is being done less quickly, you have a low power, which is a great time for me to bring up these LEDs, these energy efficient light bulbs here. If you look at the packaging, so watts are the unit of power. And we'll get into that more on the next slide. But a watt is basically, if you do a joule worth of work and it took you 1 second, that's a watt. A watt tells you how many joules of energy are being used up every second. So 40 watt light bulb right here uses 40 watts or 40 joules every second. 6 watt light bulb here, if you can see that, 6 watt light bulb uses 6 joules of energy every second. So what this LED does, an LED is a different way of making light than a regular old-fashioned light bulb, and it's much more efficient. So an LED only needs 6 watts of power to do what an old school light bulb needed 40 watts of power to do. So that is much more efficient because when you have one of these LEDs plugged in, you're using 6 joules worth of electricity every second. Whereas before you would have needed to use 40 joules of electricity every second. So that's when we're talking about wattage and LEDs and energy efficient light bulbs and all of that. That's what we mean, is how many joules of energy are being used up every second. And that's where you can see down here it says saves you money. That's how they're allowed to make that claim, is because they're saving you electricity. Again, exactly what we just talked about. Power is just work divided by time. It's the time derivative of work. Trying to give you guys that calculus language again. Even if you didn't watch the calculus video to learn how to actually do the calculus, you at least know the language. So when we look at how something is done over time, how quickly something's done, that's the time derivative. So again, you take how much work was done divided by how long it took to do it. That's your power. Power is how quickly work's being done. Units are joules per second, because again, work is in joules. It's an energy measurement, and time is in seconds. So joules per second is power, which we call watts. So watts just tell you how many joules are being used every second. So this 700 Newton person, so his gravitational force downwards, I'm just going to make him our free body diagram. Gravitational force downwards is 700 newtons. And it took him 24 seconds to achieve this staircase. That's a very slow runner. Maybe not, I don't know. That's actually like 3 stories now I think about it, so that's actually not too bad. And in that 24 seconds, he's gone up a total of 10 meters. Now please note, this goes back to our dot product, right? So if we're looking, we've got gravity going straight down, pretend that's straight down. But the displacement is like this, So if we're looking at how much work is being done to overcome gravity, right? Because that's what's trying to hold Thomas down here, is gravity. So we're looking at how much work did he do in order to overcome gravity. So we need the dot product with regards to gravity. So there are 2 ways we can do that. We can either try to figure out how much of gravity is, wait, I drew that wrong. We can either try to figure out, it's annoying, how much of gravity is in this direction, right? We could try to do that, but that's very, very, very challenging math. The easiest thing to do is the opposite. Figure out how much of this displacement is in gravity's direction. That's the strategy here. So we can take this displacement and just get the y portion of it. And that is the portion we want. That's the portion that's in the same direction as the force. So we take our displacement vector and we just look at the y portion of it, which it already tells us is 10 meters. We already know that this here is 10 meters. So we don't actually know how far that Thomas ran. We don't know how far Thomas ran. We don't know what d is, because it doesn't matter. We don't care about his actual total distance. We just need that y direction distance, because that's the direction gravity's in. So now let's plug it into our equation, right? Work equals force dot distance. So work equals force dot distance. Force dot distance, remember, is force, which is 700. Displacement, I keep saying distance and I apologize. It's displacement, that's the vector form. So there's our force. Our displacement in the y direction is 10, right? That's not his actual displacement. We don't know what his actual displacement was, but that's the part of displacement we actually care about. And then cosine of the angle between them. So what's the angle here between y displacement? So again, 700 was going straight down. This 10 here is going straight up. What's the angle between those? 180 degrees, right? It did a 180. They're pointing exactly opposite. And remember, cosine of 180 is -1. So 700 times 10 times -1 gets you -7,000. -7,000 joules of work done by gravity. Because remember, right? We were looking at gravity here. We were looking at gravity. So in order to overcome gravity, Thomas is going to have to do a positive 7,000 joules of work, if that makes sense. So gravity is trying to hold him down with 7,000 joules worth of negative energy throughout this journey. So to overcome gravity, Thomas is going to have to resist that with the positive 7,000 joules, because Thomas's force is up. So Thomas's force is in the same direction as displacement. Gravity was the force in the opposite. So again, positives and negatives, it's really more of a logic problem. I'm not really going to be able to sit here and say, yes, this is positive and this is negative. You've got to think it through. What is the work being done by Thomas? Look at the situation. Thomas is pushing up. Thomas is going up. Hence, he must be doing positive work. Thomas is going up. Gravity's going down. Opposite directions. Gravity's doing negative work. So gravity has done this negative work, and because of that, Thomas had to do this positive work in order to overcome it. Now we want power, and we know that power is simply equal to work over time, which in this case is 7,000 joules divided by 24 seconds. And that's not exactly a mental math problem, so let's plug that in. And you get a little less than 292 watts, let's say. 292 watts. Now be careful, because capital W is the algebra variable for work. W is also the symbol for watts. So kind of like how M means meters and it also means mass, W in an equation means work. W as units means watts. So don't get confused by the W's. But 292 watts done by Thomas here to get him up those stairs. A total of 7,000 joules of work spread out over 24 seconds to get us 292 watts. And then, you know, this one I'll let you do more of if you want more practice, but I don't need to waste your time going through it step by step. It's the same. It's all the same. So I will allow you to pause the video here before I put up the answers here in a few seconds. Please pause the video if you would like, but answers are coming now. There you go. So I certainly hope you found that useful. It took a little longer than I meant for it to, but that's okay because it was very, very valuable. I taught you a whole new math concept here in addition to a new physics concept, and we got that all done in 42 minutes. So there is a short practice homework. I promise it's one of the shorter ones. There won't be much dot product and that sort of stuff on it. It's pretty much just going to be force times displacement. They're going to be going the same direction in most of these practice problems, or they might be going opposite directions. So just remember, if something's going up and the force is going down, that's a negative work. So if force and movement are going opposite directions, that's a negative work. That's something you're going to have to remember. Other than that, it's pretty much just force times displacement. And then you just have to look and see, are they going the same direction for positive? Are they going opposite directions for negative? I'm not going to be throwing any of these cosine ones at you because we only had one day to learn it. So please get your exit ticket done to get your 5 points for today. I have a little homework for you this evening, and I apologize for that, but we're out of time. You know, we lost a week because we moved finals up a week to give you guys more time to work on finals, which is great, but that means I have less time to work with you guys on this stuff. Last year we actually did this lesson on May 6th, so we're a day ahead of last year, amazingly. But we just got to rush because finals are happening a week sooner this year than they were last year. So we've got to rush through it a little bit. So please message me if you have any questions. If you have too much to do tonight to get that homework done tonight, I guess that's okay. Just get it done tomorrow. Get it done as soon as you can. And have a great day.